At our given excitation frequency of 60 Hz, a 15.5 microfarad capacitor will present a complex impedance of roughly 171.1 ohms at an angle of negative 90 degrees. Application of Ohm's law demonstrates that each power factor correcting capacitor will draw approximately 701.2 milliamperes of current and lead supply voltage by a relative 90 degrees. An application of the AC power formula demonstrates that each power factor correcting capacitor will experience 84.1 volt amperes of apparent power, of which 0 watts is directed towards real power and negative 84.1 VARs is being directed towards a reactive interchange. When considered as a matching pair, you'll note the power factor correcting capacitor is slightly undercorrecting the matching winding. As such, we might expect there to be a small exchange of reactive power with the source. This being said, it's not too much, but we should expect line current to drop and become more in phase with supply voltage. An application of Kirchhoff's current law demonstrates that current in each line will be the summation of current through the winding and the current through the matching power factor correcting capacitor. Substituting our given values yields source current to be 658.2 milliamperes, will slightly lag supply voltage by a relative 4.7 degrees. Source current is substantially less than our previously non-power factor corrected circuit. And here's the important part: the motor will still function as intended. A large portion of the reactive power, rather than being exchanged with the source over a distance, is instead exchanged with the power factor correcting capacitors at the point of use. As such, line current drops and becomes more in phase with the supply voltage. Let's see if reality meets our expectations for this power factor corrected system. While rotating at the rated 1719 RPM and producing the rated 1 Newton meter of torque, the current through each motor winding still appears to be roughly 1 amp and appears to lag voltage by a relative 49 degrees. As previously, each winding experiences 120 volt amperes of apparent power, of which 78.7 watts is directed towards real power and approximately 90.6 VARs is directed towards the reactive interchange. When taken as a group, the balanced Y-configured motor windings experience 360 volt amperes of apparent power, of which 236.2 watts is directed towards real power and 271.7 VARs is directed towards the reactive interchange. From the perspective of the mechanical performance of the motor and the electrical performance of the windings, it's as if nothing has changed. Let's now consider the electrical performance of the power factor correcting capacitors. The voltage across each power factor correcting capacitor appears to be 120 volts, and the current through each power factor correcting capacitor appears to be roughly 700-ish milliamperes. Current through each power factor correcting capacitor appears to lead voltage by a relative 90 degrees. An application of the AC power formula demonstrates each power factor correcting capacitor is experiencing approximately 84 volt amperes of apparent power, of which 0 watts is directed towards real power and negative 84 VARs is directed towards a reactive interchange. When taken as a group, the balanced Y-configured power factor correcting capacitors experience 252.3 volt amperes of apparent power, of which 0 watts is directed towards real power and all negative 252.3 VARs is directed towards a reactive interchange. Here's where the magic happens. Line current, the summation of current through a motor winding and a matching power factor correcting capacitor, appears to be roughly 660 milliamperes and only slightly lags voltage by a tiny, almost immeasurable amount. From the perspective of the source, it appears as if only a small amount of reactive power needs to be exchanged over a distance. An application of the AC power formula demonstrates that on average, each source is supplying 79 volt amperes of apparent power, of which a majority of 78.7 watts is directed towards real power, and only 6.5 VARs is directed towards a reactive interchange. When taken as a group, the three-phase AC system supplies 236.9 volt amperes of apparent power, of which a majority of 236.1 watts is directed towards real power, and only 19.5 VARs is directed towards a reactive interchange. The consequences of power factor correction are far more evident when consider each branch impedance pair. Follow this sequence. Current through each motor winding still lags voltage by a relative 49 degrees. Current through each power factor correcting capacitor leads voltage by a relative 90 degrees. Line current, the summation of winding and capacitor current, drops and appears to be almost in phase with supply voltage. Can you dig it? When power factor corrected, the source stays out of it and lets reactive power slosh back and forth at the point of use. The source only needs to supply the real portion of power and line current drops. It should be noted that this system will remain power factor corrected in one scenario only. That scenario being when the motor is operated at the rated condition and rotating at 1719 RPM and producing exactly 1 Newton meter of torque. If the mechanical power requirement increased or decreased, we might see a corresponding shift in reactive power consumed by the motor, and this may under or overwhelm the ability of the power factor correcting capacitors to keep the reactive interchange at the point of use. For example, if the motor consumed less positive VARs of reactive power, we might expect current to start eventually leading voltage, since the power factor correcting capacitors are effectively overcompensating. Whereas, if the motor consumed more positive VARs of reactive power, we might expect current to start lagging voltage, since the power factor correcting capacitors are effectively undercompensating. A more sophisticated power factor correction system might actually use an adjustable capacitor, or an array of capacitors that can be switched in and out as reactive power requirements for the system change. However, these types of systems would be costlier to implement. Oftentimes, a static configuration of capacitors, sized for the most common condition, i.e. when the motor is operated at the rated conditions, is the simplest means of power factor correction that meets a majority of needs at the lowest cost. Alright, that's about it for today. In conclusion, this short lecture examined an application of power factor correction for a 3-phase AC squirrel cage induction motor. We compared and contrasted electrical properties of the non-power factor corrected motor and the power factor corrected system. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.